Okay, so we found the magnitude of the tension, which is 11.8 newtons. Well, what about okay, so let's look at block 2. So block 1. Okay, let's just number it. Oh, let's look at what?
What?
Oh, I looked at the question.
I thought I forgot my glasses.
Oh.
Essentially.
So much action.
You're so nice, buddy.
I brought her yogurt.
So, if we're going to compare the forces, so we have the forces of block 2, which are all in the y direction. Which forces of block 1 do you compare?
The X direction?
The X direction. Let's look at that.
Just like.
So that's going to give us the X component of the gravitational force. Tension equals 0. We have our X and Y directions set for their positive directions, which is going to give us the X, T, 0. So, what we want to figure out here, does that gravitational component equal the tension? So let's see if it does. What is M1 mean?
3.8 kilojoules.
Let's put it on a component. The 3.8 kilograms. 9.8 meters per second squared. 930 degrees. Well, this gravitational component is 18.62 newtons. So that's not the case. What we find out, your M1, your X component of your gravitational force is larger than your tension. So this is our first clue. We know that that X component of the gravitational force is going to be larger than the tension. And so that tells us that probably going to move down the ring. Okay. However, there's a friction force. Now we know if it's moving in that direction. The friction force will be pointing that way. So then the question is, will it move at all? We can get an approximation of static friction by actually calculating our kinetic friction. So what is kinetic friction? We're going to calculate this to see how large that is.
Wait, can you scroll back up a second? Okay, that's all.
Okay, so we know we're going to need the normal force. These one are positive and negative directions. Normal force minus M1 Gy. For the numbers. We end up with a normal force. 32.26 newtons. So then let's calculate the kinetic friction of this system. The problem told us that the coefficient of kinetic friction, 0.18, for normal force, so we're getting a kinetic friction of 5.8 newtons. Okay, so the question is, will this friction force be enough to stop the block from moving? Now, we already know that the X component pulling on the block down the slope is greater than the tension pulling backwards. So that tells us that it's very likely moving. Let's go ahead and compare this friction force. What would we compare it to? Yeah, so we're gonna have to look at the sum of forces in the X direction on the block to see what that magnitude is. Let's see. So remember, we are going to have tension so you can either do with our positive and negative directions. I can multiply everything by a -1. And so then the numbers that I have for this, 18.62 newtons for the X component of the gravitational force, minus 11.8 newtons. I don't know why I'm setting all this to 0. I shouldn't have done that. I'm just comparing these two. So when the tension and the X component act against each other, there is still a magnitude of 6.82 newtons pulling the block down the hill. So that tension force didn't completely stop it. And then you notice (6.82 newtons pulling the block down the hill is greater than the friction force of 5.8 newtons trying to stop it. So in the end, this system will move. It will move down the ramp. Okay, that was part A. Let's look at part B. Find the acceleration of block 1. We're really hoping that friction force and the difference of the X components were the same number. That way the acceleration would be 0, but not the case, so you have to figure out what it is. What is the acceleration of block 1? Okay, so for mass 1, that's the block on the ramp. We're going to look at the sum of our forces in the X direction. Since it's moving, we now have to include that friction force. And since it's moving, what does this equal? Mass times acceleration. Now you'll notice that block 1 is going to accelerate down the ramp, block 2 is going to accelerate upwards. But because they're attached by the same cable, that's the same acceleration. So your AY for block 2 equals your AX for block 1. It's just acceleration. Okay, so let's see, we'll go ahead and do the signs and multiply through by -1. So this one was set to it's in 1 x t. Friction force equals a negative. And 1 times your acceleration. So okay, so just change this to m1g minus t. Going to make it easier for us in the long run. Okay, so our x component minus t and we know that our normal force is going to equal the y component of the gravitational force. Okay, so we can get this far, but we don't have an expression for tension. Let's look at block 2. Tension. We get these signs because we set the up direction as positive y. Tension is then going to equal into A plus into G. We'll pull that mass out and we'll have A plus G. Okay, now we're just going to substitute that in for tension. And we end up with this. Now, do you think you can solve for A or you what? Yeah, so the first thing I want to do is get all of my accelerations on the same side. Okay. So you notice on the left side, I can factor out an M1G. Just going to leave sine of theta. Minus the coefficient cosine of theta. Okay, so here, move m2g over to the other side. And then over here, I have a m1 plus m2. So then in the end, acceleration is going to be that. And that's where we end up plugging in numbers. Which is a very long thing, so you try it. The acceleration should come out to be about 0.21 meters per second squared. Okay. The next set of slides. We don't have what they need. Okay, so we've been working with kinematics in the x direction. So now we're looking at a section called free fall, which is kinematics in the y direction. And you notice that the equations are pretty much identical. Well, actually, they are identical. You just change x to y. And then your acceleration, most of the time, will take on the form of the gravitational acceleration constant, 9.8 meters per second squared. You'll just have to decide whether it, the down direction is positive or negative. So the good news there, the kinematics are not changing for x versus y. Enjoy it for now, because next chapter they change to omega theta time. Okay, so one of the primary things that you want to think of when you're doing free fall, like especially if you're asked a question about like maximum height that an object will go to, one of the things that can help you solve problems is remember at maximum height, your velocity in the y direction equals 0. Because if you throw something up, there is a split second where it has to completely stop and then turn around to start falling. So at your maximum height, your velocity is always going to equal 0. That can help you solve a lot of problems. Okay. So let's see. You throw a stone straight upward. You're standing on a bridge. The stone hits the water that is 44.1 meters below the point at which you're standing. So you're 44.1 meters above the water. 4 seconds after you throw it. How high above the bridge does the stone go? if you dropped the stone instead of throwing it, how long would it take to hit the water? Okay, so you can start in part A and just go through the different kinematic equations, and you can find that you don't have enough information for any of the kinematic equations. So the first thing we want to do is figure out a total time of flight. Okay, so a diagram. We know that's 44.1 meters. Something else that's going to be important is I'm setting that as y equals 0. So then if you're doing your delta y, your y final is 0. Your y initial is 44.1 meters. Okay, so like for example, so let's see. I'm going to set positive y in the upwards direction. Let's see. So we're trying to figure out initial velocity. The total time of flight is 4 seconds, and then your acceleration in the y direction is going to be negative g because we set up as the positive direction. Okay, so let's figure out how we can solve this. Well, what is the initial velocity of you throwing the rock? I'm going to pick that kinematic equation. Now, this may seem counterintuitive because, again, we're looking at the total time of flight of 4.0 seconds, but that initial velocity is going to affect how high it goes. It's going to affect, so if it goes higher or lower, it's going to affect the time of flight before it hits the water. So it's good. You can actually use the kinematic equation based off the entire time of flight, even if you throw the object up and it comes back down and passes you and then goes below where you're at. What else is there? Utilize the delta T. And then the changes become we can do that because we substitute in the negative g. And from here, you can put in numbers. You find out that your initial velocity is 8.6 meters per second. Now we can figure out the maximum height. And we can do it using the kinematic equation without time, because otherwise we'd have to solve for the time of flight from when you throw it to when it reaches its maximum height. That's just extra steps.
Why did you change it from addition to subtraction? You have delta y over delta t minus 1/2 ay delta t.
Because I substituted in negative g for the ay.
Okay.
I have a question. When did we get rid of our square?
Oh, so when we, so here, I divided through by delta t.
Oh.
So delta t squared divided by delta t is just delta t. Okay, so part A. I chose this kinematic equation. Hang on, that's not helpful. There we go. Because I don't want to solve for the time of flight to the apex of the flight. We have the total time of flight, so it's the water, but I have to solve for a different time when it hits the apex, and then I have to figure out how high that is. So it's extra steps. Now, you throw it at the apex of flight, the final velocity is 0. I'm going to go ahead and put it in the negative g. It's going to be a negative 2g delta y. So in for delta y. The initial velocity squared over 2g. And you should get a delta y. About 3.77 meters. Now, what about, well, part B says, if you just dropped the stone instead of throwing it. So I'll show you the kinematic equation I picked, and then we'll talk about how we can simplify it. So if I don't throw the stone, but I just drop it, what's different about its initial velocity?
It's going to be gravitational, that 9.8.
Well, it will be, but what about its initial velocity? 0. If I'm not throwing it, I'm just dropping it. And so then, for delta y, substituting the negative g, 1/2 g, t squared. Let's see. Delta t squared is going to be a negative 2 delta y. And solve for delta t. So you get negative 2 delta y g. Through the whole thing. And that's why I draw the brackets, because I don't draw good square roots. Now, this may look odd at first because it looks like you've entered into imaginary space. Which was just back when they first discovered it was just called imaginary space. It's an actual real dimensional space that exists perpendicular to the one you live in. You ever seen Stranger Things? The Upside Down? Kind of like that.
When's the new season come out? Pretty soon,
I
right?
don't know.
I think it's in October.
Oh, yeah. Your Thanksgiving.
So what we're gonna get. See, that's when I drink too much coffee. All my lines are. So how does this actually work out? I get a -2.
Real quick again, why?
Because we're just dropping the stone this time. So it's initial velocity 0.
November.
Yeah, that's okay.
You end up with a delta t, so the time from being dropped to the water. That's 3 seconds. What?
Honestly, I was just.
Now, we worked on kinematics in the x direction. We worked on kinematics in the y direction. What kind of fun do you think we're gonna have next?
Combining them.
Projectile motion. Oh, we can do the z direction if you want to, but then instead of a graph where you have quadrants, you have a 3-dimensional space with octants. Then you'll have to deal with positive or negative of x, y, and z. We could go relativistic where time becomes the fourth dimension.
I had J hat. A hat.
coming at me?
Yeah, okay.
Yeah.
So, you can also have fun with quantum mechanics. You just throw the stone upwards and there is a non-zero possibility that it actually doesn't come back down at all.
That's because I called it. Hear me out. Start this way.
Okay, so projectile motion. Now, one of the things that you're gonna have to pay attention to.
We're done.
All about.
How did they just kick it?
That's how you fix everything. One of my friends in college on his computer monitor, he had an X drawn on it that said slap here. It was amazing. It worked.
They know you at the IT help desk.
Why?
Because I went in the one day and I thought we had a little projector trouble and they were like, was it Clint ever? And I'm like, yeah, did they just, and they were like, the first question, did he just try unplugging everything and plugging it back in? I'm like,
Yeah,
"That's
I've started
exactly
doing
what
that
he
now. Sometimes people come in and they're using the air tame and they start hitting the buttons on the box down here and they don't change it back.
No.
So there's some kind of different combination of buttons hit on the box down there. But it's always an issue. But one of the things you're going to have to start paying attention to is now our initial velocity vectors. You notice how you have an angle of elevation of that velocity. You also notice how your final velocity can also have an angle on it. A lot of the times we're going to be working towards these systems where you're looking at the apex of the flight, where your velocity in the y direction equals 0. And while we're solving these, especially just getting to them, one of the great things is what would the acceleration in the y direction be? What would the y acceleration for a
Go like
projectile?
positive and negative.
Do what?
Wouldn't we have to
Zero.
have a positive and a negative?
Well, we could, yes, because we're gonna have vectors now.
Should be 0.
So, do what? Well, okay, so if you set the negative direction down, yes. So the y acceleration is gonna be gravity. What about the acceleration in the x direction?
It's gonna be your initial force.
Well, because right now you don't want to do, you don't want to do drag, anything like that. We're not going to get into differential equations in here. But what do you think? So if you're neglecting like air resistance, stuff like that, what is the acceleration in the x direction?
Force at which you throw it.
0.
Why?
No, y is gravity.
The why,
Oh,
dude.
Because we're neglecting the forces that can slow down the projectile. So in the X direction, so if it's moving this way, we're gonna neglect air resistance. So your acceleration is gonna be 0. So for example, you see your V initial X, that we're gonna be working with systems where that equals your V final X. The apex of flight, you're gonna treat it like free fall. So essentially, you're gonna be doing the last two sections together. You're gonna work the X direction, then you're gonna work free fall, and then you're gonna put them together. W350G times.
Yeah, I played football. You played football. No, he played football, but I think he wrestled.
Oh, okay.
The way he.
Yeah, okay. That makes sense. Yeah, you can do that.
Like anyone that ever wrestled. Yeah, he's great about it. I like Coach Freeze, but he's I'm talking about me. You wouldn't have to ever wrestle this.
I prefer personnel.
Easy.
Pueblo and New Mexico, Ohio.